So now it's time to get into the implementation of the Oracle. That's where we left it in part 3. Basically the subdivided, how they call it, the subdivided phases implementation that gets rid of the others. And so we're now getting into the actual Oracle implementation. Yeah, so let's see, the Oracle implementation. But that's the Oracle, isn't it? Yeah. Okay. So there's now going to be a, I don't know, a, let's see, what is this implementation that they're going to discuss? Yeah, because I just did my own idea here, and now, okay, so when the theta is not 0 or pi, the sub-oracle in equation 8 consists of the following gate sequence. So, uh, XB controlled rotation, of Z, XB, XA control rotation along the Z axis, XA. Due to the limitations of the current IBM Q processes within the framework of CHASM, we need two control X gates and single qubit gates to execute a control Z gate exactly. Two control X gates and a single qubit gate. So this is basically what I did here, right? But you could. So what this is saying is that you could actually replace that with a control Z. Would it work? No, because it's not the effect that you want. It's control. Aha, so this is the. So this is what they would propose, okay. But they're saying basically that you gotta do it like I proposed because of the limitations. Am I right? Of CHASM. We need two control X gates and single qubit gates to execute the control. Here the error values on single qubit gates are on order of magnitude, on 1 order of magnitude smaller than that of 2 qubit gates. Therefore, we focus on reducing the number of control X gates and the number of single qubit gates, such as U3 gate is basically not a problem. Okay, so what they're saying is the assumption here is the errors caused by controlled operations are higher, the error rates, so you should try to minimize that. So that would not be optimal because you've got for each for each sub oracle you've got two controlled operations. So what they're saying is that this would be equivalent to doing like these. Is that correct? I'm not so sure. 60 degrees. 60 degrees. Here you've got. I'm not so sure that's. I'm not so sure that is. Okay, so there is a bit of a different thing here. That's definitely not working. Oh, you gotta uncompute that. So basically, hence we approximate the whole sub-oracle with two control X gates and 6 U3 gates by KAK decomposition 1819 as shown in figure 7. The error level of a controlled X gate of the latest IBM Q processors used in this paper is about 1% at best. Hence we approximate this oracle circuit with two control X gates. So now it's time to take a look at these a bit more in depth. So this is the, I guess, the ideal. That's how they would, that's how they approximate it. Um, hmm. Let's take a look. So let's take first a look at the upper part. So what is going on here? Maybe I'll. So. Is this an RZ gate or is this a Z gate? That's I keep having problem with that. Let's see. First of all, let's try to see if that works. The way this is, assuming that's a Z gate. So assuming that I do these and then, you know, and then we basically do uh, these. There's these controlled gate, and then there's another X gate. And now we take a look at the amplitudes here. So and the phases. So basically, that's for the 2 qubits that are in the rightmost side. So 0, 1, there's one cat, 60 degrees. 1, 0, there's one cat, 60 degrees. 60 degrees, 60 degrees. Here there's no cat. Here there's no cat. Here there's no cat. Here there's no cat. That seems to work. What if I do it here? So now, because what this is basically saying is, okay, so it's kind of saying you negate the qubit on the top, right? So what we're doing here is, if we paint all our possibilities and say this is the this is the this is the qubit that we're negating. You basically wanna, okay, so from one, so this first pass, basically what it does is it flips the cases where you've got a 1 0, right? Because you're flipping the 0, and so you're flipping that qubit into 1, and so that 1 1 combination with the control Z will actually rotate you. And that second pass here is going to do sort of the opposite, the mirror, right? So it's going to take a look at these and it's going to then kind of catch that pattern in here. Okay, fair enough. So that's the reason it works. Now, I keep getting confused with the RZ gates and the Z gates rotation, because the way here the way it's put in Quirk, right? The RZ gate says rotates around the Z by an angle in radians determined by a formula, but it's actually phasing both the 0 component and the 1 component, whereas the Z rotation, it just phases the 1 component, but adds a global phase. So does this, okay, so does this work with the RZ gate? I mean, here we've got an angle, right? So here I'll say pi thirds. And I'm going to use it here. Yeah, and it doesn't. So it doesn't because it's also flipping the So this is something that I'll definitely share. I mean, this is something that keeps confusing me in terms of notation. So the RZ versus the Z gates, and I should maybe make another video on these at some point, because it keeps confusing me. So this is should be a Z rotation, not an RZ gate. So I'm assuming that in the rest of the paper, whenever I see RZ, it really should be a Z rotation. That's V2, right? So I'll it's maybe just a matter of convention. I don't know. But that definitely doesn't seem to work with RZ, unless if I say again 1/3, 1/3. No, I mean rotates around Z by an angle in radians determined by a formula, and I'm using pi divided by 3, where these says rotates around the Z by an amount determined by a formula. So yeah, I don't know. Might be just a notation thing. Anyway, let's go ahead. But that works. It kind of checks both ways. But still, it seemed like my previous implementation also could work, right? Anyway, X control RZ. And so now this is equivalent to that. Okay, so let's take a look at this. This is equivalent to that. The one thing I don't get is the whole point here is made that okay, due to limitations. Okay, so due to the limitations of the current IBM Q processors, so in order to implement a control Z rotation, you would need two control X gates. Okay, but the error values on single qubit gates are 1 order of magnitude smaller than that of 2 qubit gates. So the focus is minimizing that. So these basically, okay. So I think what this is doing, is basically replacing that with something that does like a Hadamard style rotation. Then it turns that into control X, and then the inverse of that, right? So what is the U3? The U3. So this is something that I can't do here, but I need to take a look at the IBM Q experience, because the U3 I think this is just a parametrized rotation through the different angles. Why? That's funny. Why are those here numbers and not just? I guess it's a mistake. No, why? 2.32. So the U3 gate. So IBM Quantum Experience U3 gate. Let me sign in quickly, or log in. I used to have a login. Qiskit documentation. Using the circuit composer. Okay. So let me quickly log in. I'll pause this. So now I'm in. There's still all my old stuff in here. What was quick test? Interesting. So the U3 gate Gates closer. Okay. Oh, nice. Oh, that's definitely nice. Blocks your rotation. Okay. So the U3. Okay, so each of the parameters is the angle you rotate in one particular axis, or what? It would be cool if you could actually, if that would be interactive. That would be nice. U2, okay. Pi divided by 2, pi divided by 2. So the U3 gate, basically, learn more about quantum gates. Need to, it's difficult to find things. Quantum gates, I think it was something here, and then you've got like a U3. Oh, here you go. So the single combined downs the physical gates. Let's have more look at them. The most general is this one. This has the effect of rotating a qubit in the initial 0 state to 1 with an arbitrary superposition and relative phases. So the U1 gate is known as the phase gate. It is essentially the same as the RZ lambda. Its relationship with U3. It's this one. The U2 gate has the form. Because that's the most general form. So theta. Does this mean that this is just a like this is the z-axis parameter, this is the y, and this is the x, because the U2 is like 0 pi, so it's a pi rotation. It's a pi rotation. I'm just confused. I'm just lost. I used to know better how to navigate this page, but okay. So this seems to approximate. This must approximate a NOT gate. U300 pi. No, this cannot approximate a NOT gate. You know what? I'll just get into the composer quickly and see if I can play with the U3 gate. What I can, yeah, here. So they changed that a little bit. It's pretty nice. Chasm. I just won 3. I just really won 1 qubit, really. And so if this is 0, 0 pi, okay, that's a phase rotation. Yeah. state vector, measurement probabilities, density matrix, state vector. In yellow meant like 100 degrees, it's pi. So that's okay. So that's a you know what? I'll copy. I can use this one. So can reason. So that's interesting. That's a Z gate. That's a Z gate. Pi minus pi divided by 2. Pi minus pi divided by 2. It'll be cool to see the blocks here as well. See what kind of rotation this is. But maybe I should just go and compute the matrices by hand, so I understand what these rotations are. Approximation of, maybe I should read actually. Approximation of the SAP Oracle circuit using KAK decomposition at pi divided by 4. With theta as pi divided by 4. Okay. The approximation accuracy. The approximation accuracy is over 99%, and the average error of the CX gate of the Q processor as of January 2020 is about 1%. Until the control X gate error is half, the total error will be dominated by the 2-qubit gates. Okay, so this is an existing method to decomposing stuff. It's the KAK decomposition. Maybe I should take a look at that to understand better why, because this is really so maybe I should have started here. I feel a bit like that's a weird way. So basically, that's a really interesting way of decomposing this stuff. Okay, KK decomposition. So there was a reference that is 18 and 19. Maybe I should jump into this. 18 and 19. KK decomposition. Okay. Maybe let me just first Google KK decomposition, because even if I compute the matrices, I still don't understand. I would not understand why those rotations approximate that circuit. So that's an international Cartan's KK decomposition. I don't know if this is these. From Robert R. Tucci. The two references here are different, so maybe I should just Google that. An average of 2-qubit computation in 23 elementary gates or less. Our techniques rely on the KK decompositions from Lie theory, as well as the polar and spectral symmetric Schur matrix decomposition from numerical analysis. They are related to the canonical decomposition of the qubit gate with respect to magic basis of phase-shifted Bell states. We extend this. Oh man, is it from Stephen and Igor? Is this the? No, that's not. Oh yeah, Bullock and Igor. Yeah, that's the paper. Of course, can't get access to it. But so let's take a look at International Cartan's KAK decomposition of QC program for QC programmers. The display results presents no new results. Its goal is purely pedagogical. A special case of the Cartan decomposition has found much utility in the field of quantum computing, especially in its subfield of quantum compiling. The special case allows one to factor a general 2-qubit operation, another one of U4, into local operations applied before and after a 3-parameter non-local operation. In this paper, we give a complete and rigorous proof of the special case of Cartan's decomposition from the point of view of QC programmers who might not be familiar with the subtleties of the Lie group theory. The proof given here has the virtues that it is constructive in nature and that it uses only linear algebra. Then maybe I should take a look at this first. The constructive proof presented in this paper is implemented in some in this paper. This paper says documentation for the okay. Let's take a look at it. KK. It's 12 pages. Introduction to Cartan's KK decomposition for QC programmers. Introduction to motivation. Notation and other preliminaries. So proof of KK1. Proof. So I think QED canonical class vector. So okay, so I'll have to deep dive into these to understand basically what it means. But what this is telling me is that that step is it's simply you could think of these as a compilation problem and say, you know, that's the solution, and then that's how you would approximate it in a way that it reduces the errors. So I'm going to follow my approach and put that aside for now, and then go ahead with the virtual vertex technique here. That can be interesting, and then I'll come back to that part as well. So trying to kind of, you know, I want to get breadth first. I want to get through the paper first, and then dive into the particular point, the particular point. So here, this is one really specific point that we'll dive into this later. But it's basically, you're not like, this is not required to understand the, I think, the overall purpose of the paper. So, and then implementation of diffusion. Interesting. Okay, cool. So that's one more thing to take a look later. So what have we got so far? We've got things to come back later. The exact definition, or better, sort of understanding better what quantum volume is. That's something to come back to later. The key decomposition is something to come back later. But I think that's it basically. I'll have to catch up with my videos and see whether I missed anything, but I should probably be taking note of that. So, okay, perfect. That was not, I feel like we didn't move forward a lot. Well, we understood this idea, and that's it basically. Okay, and then the virtual vertex probably is the interesting part of the paper. The most interesting part of the paper. It's interesting. Cool. Perfect.